Okay, welcome back. So in the last lectures, we sort of elaborated more extensively about the connection between the mathematics that we have introduced to describe wave functions, and therefore the related eigenvalue and eigenstate problem inherent in the Schrödinger equation, and the mathematics of vector spaces, matrices, and vector matrix multiplication, eigenvalue problems in linear algebra. And basically, the main outcome of that sort of analysis was that the analogy that we sort of envisioned were not at all just curiosity, sort of curious similarities, but they were deeply rooted into the mathematical structure of quantum mechanics. And this became evident after we looked at a problem from a discretized point of view, and we realized that a wave function, whatever it is, has to have a finite, effectively or virtually finite support, meaning must be non-zero only between some minimum and maximum value. But in principle can go, if wave function can in principle extend from minus infinity to plus infinity, but since the integral of the wave function has to be equal to the integral of the square modulus of the wave function has to be equal to 1, then clearly the wave function must provide negligible contribution to the integral from some point on. So for all practical purposes, it is possible to find a maximum value and a minimum value beyond which you can neglect the value of the function, even if it's tiny and finite. The second piece of simplification we introduced was that of reducing, rather than evaluating the function at every point between x minimum and x maximum, we chose to discretize it and evaluate it only on a discrete mesh. And so on and so forth. Now, clearly, how many points you need to accurately represent a function with a set of discrete points depends on how rapidly the function is varying. To give two extreme cases, if I have a function that basically is flat, actually, let's take the extreme case in which the function is just a step function. Then obviously the function doesn't vary at all, and you need only 1 point to represent it. Because if you draw a line and assume that the function is constant within any of these points, or say 2 points, 1 here and 1 here, then you basically are covering the entire information there is in that function. In the opposite limit, in which the function vary on very short length scales, imagine a wave function doing all sorts of things, then clearly you need a lot of points, because if you just approximate the function in a bunch of points, then obviously you get a completely different description of the function that it actually is, that is completely inaccurate. So really, what it seems to be important to realize is that there is an intrinsic length scales over which the function is supposed not to vary, and that sets the number of points I have to use in this discretization in order for a function to be sort of reliably represented by discrete mesh. And a question that, of course, one would like to pose is, how do we estimate the number of mesh point needed. Well, normally, this procedure of estimating the number of discretization points you need to perform a calculation that in principle is a continuous calculation is a ubiquitous problem in computational science. You know, whatever physical problem you ultimately want to solve, you are likely to have just a bunch of variables, maybe a large number of variables that you want to treat. And computer ultimately can only basically process a string of numbers. So you always have somehow to go through a discretization if you want to crunch numbers. And therefore, you always have to face the problem of understanding how fine-grained this discretization should be. And let me tell you how, let me give you two answers to this question. The first question is, I start from an initial guess, and I perform a calculation. Then I perform another calculation in which I double the number of grade points, and another one in which I double again, and so on and so forth. And when I see that the result stops changing, that's where I have enough points, right? And most of the time, this is a very natural procedure. And if you think about it, this procedure is basically the same procedure that you use when you define the limit or a derivative in calculus. You take a discrete step, and then you take the jump smaller and smaller until the result doesn't change anymore on the jump you're making. That's in essence what the concept of limit is in fact referring to. Now, of course, you know, if you have zero prior knowledge about a function, it is even difficult to guess the number of points that you would like to start making calculation. And if you start with a very, 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 very wrong set of calculations, say you get very far too few points, then you would have to do many calculations in order to reach convergence, which is, of course, human and computer time consuming. In the opposite regime, you might have an initial guess of points that overkills the calculation, and you might take so much longer than you actually need. But it's also a waste of time, because with the time that you're burning, you cannot develop other projects. So it is important to have an initial guess of the number of points that you need to represent the function. That is somewhat reasonable. So I guess from this discussion, I guess it is quite clear that the number of points we need is related to how fast the function is changing. And of course, there is a mathematical object that describes how fast a function changes, and its derivative, right? So how do I estimate a priori how large we expect the derivative of a function to be? Okay, that's a typical question. We would like to estimate it based on physical grounds so that we can start off more or less with the right scale. And then, of course, we do the refinement process, increasing the number of points and monitoring that we get something that doesn't change it. Okay, so to do that, let me remind you that we have already seen a connection between physical quantities and changes in space of function. Remember, when we wrote the kinetic energy of a particle, then we understood in quantum mechanics that this kinetic energy is actually represented as a second derivative with respect to mass dimension. So this is basically telling me that the momentum is actually associated with the h bar derivative, because there are 2 powers of momentum in the kinetic energy and 2 powers of h bar. So there is a proportionality between momentum and h bar. So momentum is basically associated an operator which is proportional to this. We discovered that there is an I sitting here, but we'll get into that in a later lecture. So the derivative of a function is basically proportional to the momentum through a quantity h bar, which means that if I take the energy, I multiply it by 2m, I get p squared, right? And if I take, I'm after order of magnitudes again, I take the root, I get p. And then if I divide this object by h bar, I get something here which has the unit of a length scale. And this is the typical, sorry, length to the -1, because the derivative has the unit of 1 over length. So if I take this to the -1, will be some length scale. And this length scale will be more or less the size over which the function, the wave function, will change. So in other words, what I'm saying is that if I want to estimate more or less how rapidly a function changes, and I have an idea of the energy of the particle that is described in this function, all I have to do is to take the h bar over 2 mass times energy. And that's basically the concept of complete wavelength. Now, if I look at this, well, this is actually, say, a quantity that I can estimate based on physical constant. I have an idea more or less what is the energy, typical energy scale for a process I'm interested in with this wave function. I either have an idea of the mass of the particle in h bar, and I can sort of understand what is the typical size, typical momentum, which is the inverse length basically over which the system, the wave function changes. And so that means that the faster, the more energetic, the more momentum a particle has, the larger, the more rapidly the wave function changes. And this is completely consistent because if you remember the square world problem, in the square world problem, we had that the ground state had the slowest variation in space. The first excited state was changing more rapidly. The third excited state had more structure, and so forth. The more I was going into high energy state, the more nodes I was adding to my system, and the more nodes I was adding to my system, the more energetic I was getting. So, to summarize all this discussion, there is a direct relationship between the momentum or the kinetic energy of the particle and the length scales over which the corresponding wave function is changing. The more energy, the shorter the wavelength. And I can use this to have an estimate of how many grid points do I need to represent. I have to use sufficiently many points so that they have, for every single value of this characteristic length lambda, there will be many points. So the number of points must be larger, much larger, say a factor 1 order of magnitude more, so to say, then what? Then it must be such that the typical, so if I take the typical length, typical spacing between 2 mesh points, so I'm spacing the wave function with the quantity delta x equal to a. This is called a lattice spacing. So I'm using this typical distance to sample my wave function with discrete points on the mesh. This should be much smaller than this characteristic lambda. So if L is the size over which my system is confined, L is, say, x maximum minus x minimum. Then I have to use so many points so that this inequality is satisfied, or stated differently, the number of points must be much greater than L over lambda. And this lambda, once again, can be estimated from energy. Okay. Now we got that covered, and with that covered, what we realized last time, that the Schrödinger equation H psi equals to E psi, which is an eigenvalue problem, eigen problem, can be translated after the discretization to a matrix vector multiplication, something that goes under M, H, M, N, psi, N equals lambda or A psi M, where this psi M is a vector in a space which has as many dimensions as the number of points I have chosen to represent my wave function. So once again, my wave function here is represented by, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then clearly there is psi 1, psi 2, psi 3, which is the value of the function in each of these points. Uncovering material I already covered in the last lecture. So a function after discretization is represented by a large dimensional vector. Large dimensional because it has many dimensions as the number of points that I've chosen to represent the function. So the function is basically translated into large dimensional vector, and the more accurate that I want to be, the larger is the dimension of this vector. And the Hamiltonian is represented by a matrix in this large dimensional vector. We went even further. We were able to look at the structure of this matrix and discover that basically the second derivative was the kinetic energy was introducing a band diagonal contribution to the Hamiltonian matrix. And the potential energy was only altering the diagonal. So if I remember well, I'm going by heart, the structure of the matrix was, of course, band diagonal. On the main diagonal, I would have something like h bar squared over 2m delta x squared, or a squared, depending on how you want to call the displacement. We are using the notation a in this lecture. But there was a factor 2 and there was a plus. And the potential, and the potential u of k, if this is the kth row and kth column. In the next element on the diagonal, so to say here, k plus 1, k, you would have the same quantity, but with the 2 downstairs. And here you would have again the same quantities, but with the 2 downstairs, and a flip sign in both cases. And then, of course, you propagate this along the secondary diagonal and the main diagonal throughout the matrix. That's how the Hamiltonian looks like after you have done this discretization. Now, why do I want to do this? Why did I spend so much time into building these analogies between vector spaces and spaces of functions? Well, there are many reasons for that. Some of them are more conceptual, some other are more practical. We already glanced through some conceptual implication. Basically, what we discovered last time about conceptual implication, that based on this analogy, Fourier transformation which were used to go from, say, the X representation to the P representation, was in fact equivalent of change of basis in the associated vector space. The vector space is the vector space we use to represent this function after discretization. And basically, the structure of a Fourier transformation was that of an orthogonal, in this case, unitary. I will go into that later, the difference between unitarity and orthogonality. Anyway, a transformation in the form wave function kth component in momentum space was some kind of transformation like this. And the reason for that was, and of course the opposite thing, and the reason for that was the basically Fourier transform integrals, and integrals after discretization become sum, and that's how you get this mathematical structure. So really performing a Fourier transform to represent states in coordinate and momentum representation is really equivalent to changing the basis of your vector space through which you represent wave functions after this. So that was sort of a conceptual insight we got in this. We understand a little bit better why in quantum mechanics I have equivalent momentum and position representation, because after all, in linear algebra, I have an arbitrariness in how I define my basis of the vector space, and I can always change bases and get new coordinates to represent the same vector. So I can always change bases in this associated vector space, and get new ways, equivalent ways of representing the same quantum state. There will be more conceptual and important application of this idea of building analogies between vector space and wave functions. However, we will discuss them a little bit later in the course. In this lecture, I would like to show you one application. And this application is the numerical solution of a simple Schrodinger equation. So basically, how to use a computer to solve exactly within numerical accuracy the problem of finding the first n eigenstates and the relative eigenvalues for a one-dimensional quantum mechanical problem. So before we go into the point, we go into a simple code and we look at how it works, and then we sort of apply it and see what comes out. Let me just state once and for all, once again, the general strategy. The general strategy is to go from the continuous problem to the associated discrete problem by discretization, and then use linear algebra packages to find eigenstates, let me call it phi n, en, and related eigenvalues. So, discretization here is used, to turn a problem into a tractable problem for a computer. So, how, I want to show you a very extremely simple code that does this. There we go. If you go on my page, you'll find it downloadable right here. And we will go over it very quickly and then perform a couple of applications. So let me first state the problem we want to solve. Well, we can solve any problem with a one-dimensional potential. I'm drawing any potential here. And we know that given a potential, I have only one Schrodinger equation for one dimensional particle. Because the Schrodinger equation we want, the stationary Schrodinger equation we want to solve is this one, which depends uniquely on the potential. Yeah? So that's the problem we want to solve. And let's, be specific here. Let's consider, for simplicity, a problem we have already encountered, the one-dimensional Schrodinger equation in a harmonic oscillator. And for sake of simplicity, we're going to set all relevant units to 1. So in these units, for numerical purposes, we will see that in the code, this constant omega will be called alpha, because that's how it is written in the code, and I will not change it. Now, this means that basically the potential is one in which the typical distance through which the wave function expected to change is of order 1. And I'm supposed to be here now. Where am I supposed to be? I'm supposed to be, no, this is the presidential election. Let's see, maybe here. I'm being lost. Where is my, oh, there we go. Well, let's do it here. Okay, so we are setting all the constants to 1. This is the harmonic oscillator. And that's the problem we want to solve numerically with our code. And let me tell you, with this code, the typical momentum of a particle would be, typical energy of a particle. We know the energy of the ground state is going to be 1/2 omega h bar, right? We calculated that in the previous exercise. So say, forget about the 1/2. Say the energies that are typical of the order h bar omega, which in this case is of order 1. So we expect typical energies to be of order 1 or so. Actually, we already have calculated the ground states, and this should be really 0.5 exactly on this units, right? Now we have not calculated the excited states. And we have seen that the ground state wave function is actually Gaussian, with a constant here that you can look up in the notes. Okay, so let's take a look at the code. Now, I should begin with a disclaimer. This is written in a pre-Columbian language of programming. It's called Fortran 77. I was born in 1974. So technically, I'm allowed to use this code because it was this programming language because it was devised after I was born. But I agree that in the Python era, still relying on Fortran codes is somewhat like obsolete, to say the least. But let's not, this had in my hands and I make it readily available, and it's easy to interpret. Fortran stands for Formula Translation. So it was a language devised in the 70s to deal with mathematical number crunches. So it's still quite powerful today because it was designed to do nothing but calculations. So basically what you see here is a bunch of instruction. I don't ask you to understand the details of the code. I just want to make sense. I want to show you that all the concepts I discussed are actually present in this code. So you remember we said that it's a well-defined approximation to confine the wave function between a minimum and a maximum distance. Now he's using the letter R for distance rather than X for reasons that will become clear in a minute. But a min and a max are minimum and maximum. In this case, I have -5 and 5. Very good. And then I have a lattice spacing, which defines the fine grainness of my mesh. And this, what we call A, the lattice spacing, it's called dr in the code. And that's defined by the total distance, R max minus R min, divided by the number of points. Actually, the points -1 because the number of intervals is the number, is not given exactly by the number of points, but the number of points times -1. It's not a big deal. And this is the distance that must be much smaller than the typical distance over which we expect the wave function to vary. So this has to be a small number. Now, since everything has been chosen to be of order 1, the claim is as soon as, the distance becomes much greater than 10, 20, we should be close to convergence. This is something that we're going to check, right? So for the moment, the number of points is set here to be 80. Let's start conservative. Let's start with 30 and see what happens when we increase the number from 30 to 40, 50, 60, 80, 100, and see if we get different results. Okay, these are the parameters that we're referring to. Alpha, beta, you can forget. Alpha is supposed to be omega, the same thing. Now, here you have a discussion about dimension. It says if dimension equals to 3. So technically, this code solves the one-dimensional Schrodinger equation. But if you remember from our discussion on the classical theory of the hydrogen atom, three-dimensional problems in a central potential can be translated into effective one-dimensional problems. And so this code can either solve the genuinely one-dimensional problem or the effective one-dimensional problem that comes after reducing the three-dimensional problem into an effective one-dimensional problem. And if you remember that discussion, there is an orbital angular momentum quantity floating around. And this orbital angular momentum quantity is actually here defined in L. It stands for L, the label L, which is typical letter for angular momentum. But in this application, we stick to the one-dimensional cases. So we don't need effective potentials or anything like that. But that's why the variable that defines the position is called R, because in three-dimensional effective problems, that's the distance from the center. Okay, here is now for each of the points, you define the potential. Remember, the potential is a vector 2, is the function defined by all the values in each of the points of the mesh, right? So what you go through the mesh. I go from 1 to 0 to k, and you define the value of the potential in each point of the mesh. And if you read here, it's 1/2 mass omega square r square, which is precisely the harmonic oscillator. Here are different choices that you can play around with. You can define your own potential if you want. I don't do that. And again, if the dimension is 3, you have an effective potential here that is the famous repulsive centrifugal effective potential we discussed in the past, but let's not deal with that here. We'll deal with it later. And then what the code does is defines the Semitone matrix, which in this weird notation is called A. So it's a K by K matrix, number by points, number of points, number of points. And let's not worry for the moment for the first and last lines. Let's concentrate first to the bulk. And as you can see in the diagonal, okay, elements, JJ here, I have a kinetic energy term and a potential energy term. And the little guy that you see here is my son. Sto facendo lezione. No, non posso giocare. Allora aspetta un attimo. Sorry. Let me pause and have my go. Yeah. Okay. Sorry for that. That's how remote working and smart working actually turns out to be a smart way of dealing with kids. So here you see this is the diagonal and have both the potential and the kinetic energy contribution. And when I move to the off diagonal terms, I only have, band diagonal, one more on the right of the diagonal and one on the left of the diagonal, and they're the same, they have the opposite sign, and they are smaller by a factor 2. So really, this is what you expect this to be from the analysis. Okay, I'm back. So as you can see, in the off-diagonal terms, there are the kinetic energies, have the opposite side. And now let's worry about these two parts here. They are there because when you have a matrix, you know, in the corner, you get some exceptions. In particular, while a typical element has a right neighbor and a left neighbor, and then zeros everywhere, when you are in the upper corner, so in the element 1, you only have a right neighbor and not a left neighbor. But when you're in the bottom right corner, you only have a left neighbor and not a right neighbor. So let me show this by this diagram. Here you have a left neighbor and a right neighbor. Here you have only a right neighbor, but the left neighbor is outside the matrix, so you don't have it. And here you have only a left neighbor and the right neighbor falls outside the matrix. And everything else is actually supposed to be 0 in the Hamiltonian matrix, right? So if I go back to my code, you see this, that in the left neighbor I have only 1, 1 and 1, 2, and of course I don't have 0, 1. And in the right neighbor, right corner, I have k, k minus 1, and kk, but I don't have k plus 1 because this is not there. Yeah. So, and then finally, all I have to do is to call a subroutine, which is called this way, in which takes this matrix and computes the eigenvalues and eigenvectors. And then the rest is basically print out the potential and the eigenvectors. So just to be sure that I recognize the format, somewhere here it says how it's calling the eigenfunctions. The file is called eigenvectors, right? And in the eigenvectors, the first line is going to be, the first column is going to be the position. Then there's going to be the first 1, 2, 3, 4, 1, 2, 3, 4, 5 eigenvectors. Okay. Okay, so what am I supposed to do? I'm supposed to compile this code and to run it. And already we see something quite interesting. Already with such a small number of points, the ground state is quite remarkably close to the exact result. We expect 0.5 and we get 0.4967. So we only say 1% far from the exact result. Now, as we move on, we see other numbers. Now, let me tell you that the harmonic oscillator is a particularly instructive example because the entire spectrum can be solved exactly, not only the ground state. We only computed the ground state. But with slightly more advanced method, one can get a hold on the entire spectrum. And let me tell you that the result of such calculation is the following. So we already, this is the result for the entire spectrum. So if you look at it, it means that n equals 0, E naught is equal to 1/2 omega h bar. N equal 1 is equal to h bar omega times 3/2. N equal 2 is h2 is h bar omega 5/2. So basically what this is telling me, I expect to be 1/2 h bar omega here, and then h bar omega between every state up in the spectrum. So this very nice problem is very symmetric, and as a result, the spectrum is equally spaced. The distance between En and En minus 1 is always h bar omega. Now, if I look at this, I see that in fact, since h bar omega in these units should be 1, if I take the second E2 minus E1, I get roughly speaking 1. And if I take the 4 minus 3, I get something close to 1. But as you can see, as I move higher and higher in the spectrum, the accuracy gets worse and worse. For instance, let's look at E6, negative 5. This is 5.29 minus 4.36. So this is actually not very close to 1. Is off by some 5 to 6% or even 10% actually. So on the other hand, we saw that E1 minus E0 is actually off by very little. It's off by basically, it's 1.48 minus 0.49. This is only off by 1, right? So as I move up in the spectrum, the approximation is getting worse and worse. And the reason is that as I move up in the spectrum, the kinetic energy of my particle is larger. So the derivative of my wave function is supposed to be much higher, because remember the kinetic energy measures the second derivative, and the momentum grows with kinetic energy, and the momentum measures the derivative. And if the function has higher derivatives, and it's basically defined in the same box, it means that the typical length scale over which the function changes becomes smaller and smaller. So as I go higher and higher in the spectrum, my discretization step becomes less and less, much smaller than the typical length over which the wave function changes, and therefore my discretization becomes more and more error prone. So if we do things carefully, by just maybe doubling the number of results, we should see a much better agreement with the expected result. So let's do that. Let's Emacs the code. But this time, rather than using 30 points, let me use 60 points. And I resolve it again. Okay, now you see things are getting much better. I'm getting very close to 1/2 now here, 49 and 49. Before the two numbers were not the same. And I'm getting only a variation of the second digit here for the last two. Let's do it one more. Now, rather than 60, I'm using 160 points, maybe 120 points. Okay, now things are much more under control, but they're not quite perfect. Maybe this is because we decided the function was to be dying at 3, if I remember well, n minus 3, 5 and minus 5. Let's try 6 and minus 6. Now, if I do 6, clearly the discretization is increased by 20%, so I should increase by 20% this also. So let's remain with the same level of limit. So let's do this. And now everything becomes basically there. Look, we are looking at the second digit now. So you never get to 0.5, period, because this is a numerical calculation. So how do the wave function look? So let's look at the file. Remember, the first line is the x-axis, and then are the different eigenstates. So let's use, for instance, plot eigenvectors using 1 and 1. This M2, this is the ground state. What you see is the negative Gaussian. Hold on. Didn't we say that the wave function was supposed to be a Gaussian and not a negative Gaussian? Well, remember, the wave function is to be normalized with the square modulus. So from all practical purposes, this wave function and this wave function with a negative sign represent the physical state, because the physical state only measure the square modulus of the wave function where the sign disappears. So when the code is asked to find these eigenvalues, it can find either of them, but it makes no difference from the point of view of physics. So you can flip this if you don't like it, but it's basically the Gaussian that we saw before. So let's look at the first excited state. That's what it looks like. Again, the relative sign is irrelevant because we might take the square. And see what happens as I get the next excited state. I get a node in the wave function, as I would expect him to find. Maybe we can actually plot this together with U point up, which is the potential. Okay, now the potential is basically killing all the structures, so let's not do that. Always set y range minus 1. There we go. Now let me go to the next steady state. And again, you see 2 nodes now, and so forth and so forth. So there's another interesting thing that happens. Maybe it becomes clear if I compare this with the ground state. You see, the ground state is confined within a region, say, between -2 and 2. While the second excited states extend to, say, up to -3 and 3. Why is that? Well, that's exactly what happens, what you expect from phenomenology. You have a potential. If you're moving at this level of energy, physically, you should be confined to these 2 points. There are tails, so the wave function extends a little bit beyond these points. But if you're moving in this energy, you're in the second excited state, you should be physically confined within 2 points and maybe a little bit of tails outside. So you expect to be oscillating with a broader range of oscillations. So there we go. This is what it is. Okay, so you can play around with this, have fun, and entertain yourself in solving the Schrodinger equation for arbitrary potential. You see why it is so important to understand the connection between linear algebra and mathematics of quantum mechanics. And later on in the lecture, we will go much deeper into that to define what is called a Hilbert space. But let's not run too much ahead. Goodbye.